As a summary of this session, we studied the subparticles present inside the nucleus. We have protons and neutrons in the nucleus, which is a very small area in the atom, and around we have electrons in motion. Till now, we did not know what is the type of this motion. We proved later that the motion of these electrons can be associated to a wave where lambda of the wave is equal to h over the mass of electrons times the speed. So if we have different electrons in the atom, the speed of these electrons are different, but the mass of these electrons are equal. So the motion of these electrons is a wave, but for electron 1 we have a wave of lambda 1. For electron 2 we have a motion wave with different wavelengths is lambda 2. Why? Since the speed of the electrons inside the atoms are different. We pass after to the description of the light. We said that the light is an electromagnetic radiation characterized by a speed, characterized by a wavelength lambda and the frequency mu, where mu is related to lambda, mu equals c over lambda. And we have different types of radiations according to domains: infrared, UV, TV, radio, ultraviolet, and visible. We are interested only in the visible domain. Yani we have to know that lambda of the visible domain is between 400 and 800 nanometers. Then we describe the experiments of Planck and Einstein. And one student asked me, what is the importance of these experiments? Einstein described that the radiation is a flow of particles called photons, and the energy, the total energy of the radiation is equal to the number of photons, which is n, times h nu, which is called the quanta, which is the energy of the photon. And Einstein's concept was proved by the photoelectric effect, which is the ejection of electrons from the surface of metallic piece when a radiation strikes the surface of this metal. Planck described that the radiation is directly proportional to the frequency of this radiation. So when a metallic piece is heated, so we have E absorbed is equal to E of the radiation emitted, E absorbed as heat equal E radiation emitted as light, which is equal to NH nu, and N is an integer value, H is the Planck constant, mu is the frequency of the light emitted. The photoelectric effect is the ejection of the electrons from the surface of the metal when a radiation strikes the surface of the metal, and the condition for the photoelectric effect, the energy of the radiation that strikes the metal should be greater than E0 of the metal, and E0 of the metal is the threshold energy, which is the minimum energy not to eject the electron from the surface of the metallic piece, is